Good afternoon, good morning, or good night, as the case may be, depending on where you are. I am Jerry Miller, and I'm here to welcome you to the session on sea level rise. We're very pleased to have attendees from dozens of nations around the world. So I will take a moment to note that most sessions will originate in English. However, if you prefer translation, please download the translation app called Interactio. It's available for free in the Apple Store, on Google Play, or via the web interface at app.interactio.io. Interactio is spelled I-N-T-E-R-A-C-T-I-O. Once again, if you prefer translation to English, Portuguese, French, or Spanish, get the Interactio app and enter the meeting code found on the conference agenda. That code is Summit, S-U-M-M-I-T. Our session is slated to run for 1.5 hours until 1:30 EDT or 5:30 p.m. UTC. We will actually stop about 10 minutes before that, should additional time be needed for discussion during that 10 minutes, we'll make a Zoom link available to all of the audience watching on the live stream so that you will be able to join us on Zoom and continue the discussion if there is desire for that. And with that bit of housekeeping done, I'm pleased to bring you an amazing group of speakers today. Our first speaker is John Englander. John is an oceanographer, a consultant, a best-selling author, and leading expert on sea level rise. He brings broad experience that allows him to see the big picture of sea level rise and its societal impacts. That experience includes over 30 years as a leader in both the private and nonprofit sectors, and he continues to work with businesses, government agencies, and communities to understand the financial risks of increased flooding due to the compounding effects of sea level rise, extreme tides, and unprecedented rainfall and storm surge. His best-selling book is High Tide on Main Street, Rising Sea Level and the Coming Coastal Crisis. And if I understand correctly, John, you have another book coming soon. Maybe you'll give us a bit of preview of that. And at this point, the microphone is yours.
Thank you, Jerry. Let's get this here. Make sure I'm in presenter mode. Does that look right? No?
Okay, now we see your slides.
Okay, thanks. Thank you. It's a pleasure to be here and to kick off this panel. Most of the people who follow me will give you a lot more detail and aspects of it. My role is to kind of set the stage, knowing we have a very international audience and also a very diverse set of expertise watching this program. So I presume you're not scientists, because some of you, although some of you are, of course, it's a wide range, and this is to set the stage. What's going to happen here? Hold on. That progressed to slide 2? I can't see it.
Yes, we're seeing your slide 2.
Okay. So sea level rise, surprisingly, is not uniform. Without getting into the colors here, the blue colors are less than average and the red colors are above average. But the point is that global sea level rise is what we tend to talk about, but that often overlooks the fact that sea level rises differently in different places. And as Antarctica and Greenland melt for some fairly obscure technical reasons, that will actually increase. So we need to look at sea level as a global trend, but then also find out what's happening in your part of the world, wherever you may be. We tend to think of climate change as a problem and talk about sustainability and resiliency and adaptation. I would just say up front that it's important to distinguish those three things. That to me, sustainability is things we can do in long term without degrading, like we should be reducing greenhouse gases, looking at our energy system, that's a sustainability issue. Other issues like recycling are also sustainability. Then we get into what I can term resiliency, which is preparing for the new normal, the storms, floods, heat waves, wildfires. That's
Excuse me, John, if I could interrupt. We're seeing your presenter mode. We're seeing two slides kind of side by side.
Thank you.
Maybe you need to switch screens somehow.
Yeah, let me see if I can do that 1 second here. We had that problem up front, and I thought we solved that. That should be here. Is that better?
There we go. Now we're seeing a slide with 3 bullets.
Yes, thank you.
Okay.
But I can't advance it in this mode. That's, oh, here, maybe down here. Let's try that. Is that there? Did that
Yes,
work?
now we're seeing the Arctic.
Okay, good, thanks. Thank you very much, Jerry. Okay, so we know the Arctic's melting, and we worry about the polar bear, and that the Arctic sea ice is certainly a cause of concern as it disappears, because it's going to change weather patterns. Icebergs, we're seeing more and more of those. It's important to understand up front that the sea ice and the icebergs do not affect sea level directly as they melt, because like ice cubes in a glass, they're already floating on the water. And so they're not the problem. It's the ice on land that we think of as glaciers. And as the glaciers break off into a new iceberg, that's like adding another ice cube to the glass of water, and it does raise the level of liquid. And of course, melt water from land would also raise the level of the ocean. So those are some things that, unless you really focus on sea level rise, you might not think of. The problem in terms of framing the big issue of sea level rise is primarily 2 places. In fact, 98% of the world's ice on land is in Antarctica and Greenland. So while we can look at Alaska and the Alps and other glaciers in the world, those 2 places hold a combined total of almost 65 meters of potential sea level rise. Not that that's going to happen anytime soon. Coastal flooding, which is kind of where the water meets the land, and is the broad category of concern. We think of storms and storm surge, heavy rainfall, runoff, which can multiply rainfall as it goes downhill. Then extreme tide events, sometimes called king tides or spring tides. And then rising sea level is different than those weather events and tidal events. It's a change in the volume of the ocean. And it's the primary focus here. Also, erosion often gets wrapped in with rising sea level, but it's fundamentally a different issue. Erosion happens during storms, and coastal erosion is a natural process irrespective of sea level rise. We are seeing this is a historic house that's been there for 100 years, but this is happening all over the world, that buildings which are stable and very solid are flooding where they didn't used to flood. We're seeing the wharf in San Francisco just as another extreme example. It's been there for 140 years at that elevation. It didn't used to go underwater every month as is now happening. Streets are flooding regularly with the full moon high tide. So what's causing this? Well, if we look back in a very simplified diagram, since the last ice age peaked 20,000 years ago, sea level started rising as the ice melted, and it had several bumps, as you can see here, and it got to the present level about 6,000 years ago, which for practical purposes is probably as far back as we go in human civilization as an organized society. This is the big picture of the problem, that sea level does change up to 120 meters. That was a natural event, which I'll explain in a moment. And it leveled out about 6,000 years ago. That's about the height of a 30-story building, as shown. If we look at the records from tide gauges, which is kind of our earliest global records of sea level, going back to 1850, the rate's been pretty consistent, bumps up and down, but in a trend. When we get into the satellite data, the last 28 years of information, we get a lot more precise. And from that satellite record where sea level is measured to fractions of a millimeter, we can see that it was going along at about 1.5 millimeters a year. Then for over a decade, it was over 3 millimeters a year, double the rate. And if we look at the last 10 years, it's about 4.5 millimeters a year, another 50% increase. What this makes pretty clear is the trend of increase as we had expected. This graph is something that I've put together and I will make freely available to anybody who wants to use it. It charts 400,000 years or 4 ice age cycles. And it shows at the top, green is a carbon dioxide, a greenhouse gas. Red is global average temperature, and blue is sea level. And without spending too much time on this, but you can see that there is a pattern, a cycle. It's about a 100,000 year pattern. We know what drives it. It's an orbital variation, basically, that changes the amount of heat we get on a 100,000 year cycle. It's called a Milankovitch cycle for those technical interested. The pattern is about 100,000 years. It's slight variation because of orbital mechanics. And carbon dioxide and temperature go together for two different but simple principles of physics. When the planet's warmer, there's less ice and sea level's higher. Now, the lag time for adjustment is considerable. It's decades to centuries to even 1,000 years for these to get back in alignment. But what's important is to see that they move in parallel. The peaks line up. And we were at the normal high end of all three of these lines for the last 200 years. But now carbon dioxide is shot up like a rocket, as you can see in the upper right. It's at 414 parts per million. That's 40% higher than in the last couple of million years, actually. And temperatures are climbing and sea level's climbing. So this gives us a very big picture. It's not normally how scientists look at the detail, but it does help to see the forces in the larger picture. It's worth noting in the bottom line, the blue line, that the last high point of sea level 120,000 years ago was 25 feet or 7 meters above present. So sea level gets higher than now, even in the natural world without human impact. But the fact that carbon dioxide is so warm and the Earth is warming to a level not seen in 3 million years means that we can expect much higher sea level. And the fact is, until we can bring that green line down, the carbon dioxide, it's unlikely that we can even slow sea level rise. Let's see how we're doing. Okay, wrapping up here. This is a projection of sea level. This comes from NOAA in the US, and it shows 6 different scenarios. Actually 5 different scenarios, sorry. Well, I guess 6 if you count the baseline, for what might happen by the year 2100. What most people don't stop to think about when they look at this graphic is that those are smooth lines and they're fairly evenly spaced. They're really not predictions. They're just projections to think through what would happen, but sea level doesn't rise smoothly. And it hasn't done in the past, and it probably won't in the future. We need to start preparing for abrupt change like happened 20,000 years ago, as I showed you in the first slide. For those who want more information, I do have a weekly blog post. Jerry mentioned my book, High Tide and Main Street. My new book coming out early next year, Moving to Higher Ground. It's actually already available for purchase, but it won't be delivered till April. And it's just part of telling the story for more different audiences. And I try and translate the science, as you can see, into language that anybody can understand, because we have to cross over from scientists to engineers to financiers to property owners to people who build infrastructure and to governments. And that's what I intend to do. So these are my contacts. With that, I think I'm finished. Thank you.
Great, thank you for that, John. Very important points. There are a couple of things I want to come back to during the Q&A session, but we're going to hold questions until everyone has spoken. So let's move on quickly to Richard. Richard Alley is the Evan Pugh Professor of Geosciences at our host institution, Penn State University. Richard has received honors and accolades too numerous to list, so I will only highlight that he's a member of the U.S. National Academy of Sciences, and that early in his career, he was a recipient of a Presidential Young Investigator Award. We think a lot these days about early career professionals, and Richard's story is quite a good one in that regard. To many, Richard is best known from his book, Earth, the Operator's Manual, and the public television series of the same name, for which he was the lead presenter. He's also known for his detailed studies of ice cores from Greenland and West Antarctica, and has been a significant contributor to the work of the UN Intergovernmental Panel on Climate Change, among a great many other things. So Richard, take it away.
Thank you, Jerry. It's a pleasure. And thank you, John, for getting us set up there. And thanks to all of you who have come out to join us here. And so let us see if we can't get to a screen share here, and we'll get you a little pointer and see if we can make that work. So it's an honor and a privilege to join you. And there's an iceberg. So yeah, so we do have very high scientific confidence that humans are causing warming, primarily from our CO2, and that is driving a rise in sea level. And these are not seriously under discussion anymore. They're real. The sea level rise is having impacts. And some of what John showed you there, people sometimes will call that nuisance flooding until it's on a storm surge that takes out their house, in which case they call it something else. It already is having real impacts for many people around the world. And it's very clear that even a little more rise can be a lot more danger, and the difficulties go up faster than the ocean does. And that's an important point to keep in mind. This one I swiped from the Miami Herald under free use. As John pointed out, this is not a storm. This is a high tide. And the octopus here is not from hockey fans throwing things into the arena. This swam in there, right? So this is flooding, but for Miami, this is still sort of a nuisance. But at some point, it will not be. And at the point where it goes from I can't easily drive through the parking garage to I need to invest billions of dollars to maintain my water, then the prices get different. So this comes from Bloomberg Business Week. For people who don't have billions of dollars, it's even more damaging in a lot of ways. So the sea level rise is happening. It matters. Here's a picture I swiped from a publication listed down below. This is a hurricane that did not get into New Orleans. This is New Orleans. I would not have wanted to be the peace officer. There's a bit of a hero here checking on things. A little bit of sea level rise can matter. And if you want one picture of how a little rise can matter, there it is for you. A little rise is almost certain. We are already committed to more rise. How much more rise depends hugely on our decisions, but it also depends hugely on how the ice sheets of Greenland and Antarctica respond to our decisions. And the sort of thing that you're likely to need to raise this particular wall is nearly certain. The possibility that you could drive sea level rise out of the picture is what worries me at night. Okay. So sea level rise so far, what's driving it? If you go look in the mountains, the mountain glaciers are melting. Water that used to be frozen on top of a mountain is now in the ocean. That raises sea level. The ocean is expanding as it warms, and it takes up more space. That raises sea level. And we're getting a little water coming out of the big ice sheets and into the ocean, especially from melting in Greenland. And just how important those are varies over time, but broadly, it's a third of each. We're mining groundwater in places, pumping more water out of the ground than goes back in, but in other places, we're building dams and holding water on the land, and that's sort of kind of balanced. So it's sort of ocean expanding, mountain glaciers melting, big ice sheets. Okay. The IPCC projections, the United Nations, what do we face? Something similar going forward, that all of these, the mountain glaciers, the expanding ocean, the ice from Greenland and Antarctica, will continue to supply sea level rise, driving something like a meter more rise by 2100 under strong warming, and notably less than that if we restrict warming. So that's what the UN says. But then there's this really important point, and John already raised this, but I'm going to raise it again. For that to be accurate, more than 99% of the ice in the ice sheets has to stay out of the ocean. If you melt every bit of ice in the mountains, you get about that much sea level rise. And then there's no ice left to do anything. You get sort of that much sea level rise if you warm the ocean by a degree, but it takes a long time to get that heat through the ocean. And so that's not a terribly fast thing. And as John pointed out, Greenland can raise sea level 7.3 meters, 24 feet, Antarctica 56 meters, total more than 200 feet. Now, we do not expect all of that to come, but when the IPCC says, yeah, ice sheets will not dominate, they are saying virtually all the ice in the ice sheets will stay where it is, right? Just as a scaling, here is the United States, where I am, superimposed on Antarctica. Antarctica is big. Here is Greenland superimposed on Antarctica. Greenland actually is fairly big too, okay? And having been across pieces of it, there's a lot of ice there. I'm going to show you something, a little bit of wisdom from history and how that applies to Antarctica and Greenland. So in the days before COVID, you could get in a cruise ship and go to Glacier Bay, and you could go 100 kilometers, 60 miles up the bay and see icebergs. When Vancouver, sort of the first European observations, goes by here, Glacier Bay did not exist. It was completely full of a glacier that filled every bit of this thing. When John Muir went up in 1888, less than a century later, most of the bay was open. It had retreated, you know, it's 60 miles long, it's 100 kilometers. And most of this happened fairly quickly. If we look down on this from above, here is a map of that. And Vancouver saw that the ice had filled the entire bay and it got wedged in this narrow place up here. The bed is high, the fjord is narrow, it's stuck in a bottleneck. And it's hard to get the ketchup out of a bottleneck. It's hard to get the ice out of a bottleneck. When John Muir came up, the ice had gone all the way back here on the way all the way back. And it had done so very, very rapidly. And it did not do so by flowing through the ketchup bottle outlet. It did so by retreating and breaking off. And I'm going to take you in that little pink box. So that's just a little tiny bit of what happened. We're going to look along that arrow. And this is what it looked like in the year 1941. The icebergs are breaking off right down in the corner. This is 1941 in that little box. 9 years later, there's where the icebergs are breaking off. And a little later, this is the same rock. It's the same view. And then this is a little later yet. Okay. In total, the ice retreated this 100 kilometers, 60 miles. It thinned by a mile. 1,500, 1,600 meters of thinning. It did not do that by getting out of this little gap. It did that by breaking off, going back, okay? This is Antarctica. The red is where it's already thinning pretty rapidly, and we're going to go right over here to Thwaites Glacier. If we take the ice off, these oranges up here are the Transantarctic Mountains. With no ice, that would still be a mountain range. These blues are 2,500 meters below sea level with 1,500 meters above sea level of ice. And the ice is trying to get out of a bottleneck just as it did in Glacier Bay. It's stuck in the mouth there. And if we take a different view, this is what it looks like. The flow is coming out of a bottleneck and it's like this traffic jam you see, except worse. Because Thwaites converges horizontally, vertically and horizontally. There's not another deck in this traffic jam. If Thwaites Glacier acts like Glacier Bay, it breaks off icebergs, it retreats to the next bottleneck. It's 3 meters of sea level rise. Most of the IPCC class models do not have the physics of icebergs breaking off the cliff. They don't, okay? One model that does said after we get started, if we don't warm rapidly, it won't happen. If we do warm rapidly, in a few decades it starts, and then the next 100 years you get 3 meters, 11 feet of sea level. Most of the models don't do this. The one that does is a little bit disturbing. Now, this is not certain. It's not guaranteed. There's work to be done. We can avoid it, especially if we limit warming. But that one model is not the worst case. And don't believe for a minute that it is. Okay? So let me summarize. Sea level rise is virtually guaranteed. Our decisions on our energy system and what we do to the temperature are hugely important in how much sea level rise. The uncertainties in the science, it might be a little bit better than I said. It might be a little worse. It might be a lot worse, but there's no a lot better. It is much easier to break an ice sheet than it is to build one. It is much easier to break almost anything than it is to build one. And this makes our decisions about our energy system especially important. Thank you.
Well done.
And thank you, Richard. Let's move on now to Klaus. Klaus Keller is also from Penn State's Department of Geosciences. His research includes climate change, Bayesian inference, decision-making under uncertainty, and climate risk management. He also directs the Center for Climate Risk Management. He takes a mission-oriented approach to his research, incorporating a wide range of disciplines such as Earth system science, economics, engineering, and philosophy. He too has contributed to IPCC reports and has published more than 100 peer-reviewed articles. Klaus, take it away.
Thank you. Here we go. Okay. Thank you for the introduction. Richard gave an amazing presentation, as the others. This is a hard act to follow. I will try to put this into perspective, specifically about what this means for adaptation and real decisions. When we look around the world, we see that people, institutions face hard decision problems. Richard showed already the levee in New Orleans. This is another levee in New Orleans. And you see in the upper right, they're right now repairing it because it failed. And you see that people are living behind the levee. They're walking their dog. And the question is, how high would you like to build this flood wall? That is a problem that we are facing. And the question is, what information do scientists actually provide for that? And I would like to tell a story about different sources of information and how we could assess which information is most needed and what does this mean for us designing research. So let's start simple. Let's start with what scientists produce. And I'm a scientist myself, and people work very, very hard to look at projections and predictions and have uncertainties. And this is a really beautiful figure by Church et al. And they make projections. And then, however, as Richard pointed out, there are those errors. Larger values cannot be excluded. And the story is somewhat like this. The scientists say there may be dragons. Decision makers ask, well, how big are those dragons? How dangerous are they? And the scientists say, well, it's complicated. And of course it's complicated, but an engineer at some point needs to build something and they need information. And that requires communication between decision makers and scientists. And communication means information has to flow in both ways. So the question then is, how can we improve communication between decision makers and scientists? For this, it might be useful to go one step further down the line to a stimuli that is being produced by the federal government, here the US Army Corps of Engineers. They have a sea level curve calculator. And this is for Sewell's Point, which is close in New Orleans. Oh, actually, this is in Norfolk, my apologies. And you see again those scenarios. And they go from in the past into the future, in this case for 200 years. And they even give you uncertainties around certain scenarios. For example, you have 66 percentile around the extreme scenario. The problem here is, however, that the question is, what uncertainties do you actually need? And how do you actually separate those different scenarios. What does extreme mean? What does low mean? What's the physical meaning? Here's a result produced by Vivek Krishnan, who is now an assistant professor, Richard Ellie, who gave the talk before, and myself. We translated this into the decision problem of how high would you elevate a flood wall in Norfolk, Virginia, if you have scenarios that account for water levels and reliabilities, because it turns out engineers care about not just sea level, they care about local sea level and storm surge. And you often have to build structures that achieve a reliability, for example, a 1% in a given year probability, which is the 100-year return period. What we've done here is actually very, very simple. We produced probabilistic scenarios from the given physical assumptions, for example, whether the ice sheets are melting fast and have a threshold response or not, or whether we have changes in storm surge, or whether we just continue assuming a linear case in historical cases. And it turns out that if you take the green line, which is the lowest projection, but arguably the least realistic, and you compare it with the arguably more realistic, in this case, dark red case, the 1 in 100 case becomes 1 in 19 years, or once every other decade, roughly. And so if you neglect those deep uncertainties, meaning you're uncertain about your uncertainty, this can lead to poor designs and outcomes. So the question then is, how can we actually mainstream the process to provide information that is potentially useful? And for this, I think one key concept is the issue of mission-oriented basic science. This is the beautiful concept of Pasteur's quadrant, here redrawn. And it asks a question about, is the research we do, has it a quest for fundamental understanding? Yes or no? And has a consideration of use? Of course, very few people want to be in the lower left quadrant, but the upper left quadrant is pure basic research, and the lower right is pure applied research, or for example, engineering. But the upper right is actually the quadrant where arguably much of the action has to be in order to inform fundamental research that is actually useful and can be used for decision making. So the question is here, how could we do that? And one key point is maybe illustrated by this dog picture where the dog barks up a tree, but you really don't know whether you're barking up the right tree or the wrong tree. And so the question is, you should check whether we are barking up the right tree or the wrong tree. And how do we do that? And here I think it is important to step back again and say, how do we produce science and how do we write reports like the IPCC? There's the standard approach and there is an inverse approach. The standard approach seen here starts typically with the Earth System Science or the IPCC Working Group 1, what are the stakes? So what is the physics of an ice sheet and what are projections? Then this information is delivered to risk analysis of, well, what are the risks? What's the intersection between the hazard, the vulnerability, the exposure? What are economic impacts if we follow certain strategies? And then this is, for example, IPCC Working Group 2. And then this is handed over to decision analysis, which is IPCC Working Group 3, to say, what could we do to manage those risks? However, in this process, often information that is needed in the third step, the decision analysis, is missing from the Earth System Science, and there is very little how we can feed back. So one approach is to actually invert it, to have an inverse decision analysis, to start with the decision analysis and say, what is actually driving bad outcomes, and where do we need to focus fundamental research? So to demonstrate this in the remaining 2.5 minutes, I'd like to go back to the introduction about the problem, how high to build a flood wall. This is a study done by Tony Wong, who's now a professor. And we did an analysis where we looked at the sources of uncertainty in the decision how high to build a flood wall. And we account for all the uncertainties. And then we asked the question, which uncertainty matters for driving the metric of, in this case, damages or flood hazards. And the easy part is that if it has a big bulb here, it's important. And if you barely see it, it is not important. There are technical details which you can neglect right now. But the point is that if you go back and you squint, you see many things are important, or a few, but many things have very little importance. And the point here is we want to identify the drivers of poor outcomes. And we then want to use these insights to identify mission-relevant fundamental science questions and to design research to understand those questions more. So just to be more specific, they are color-coded. And I highlighted in red here those uncertainties which are the dominant drivers. On the lower left, you see parameters about the Antarctic ice sheet. That is not surprising because that is an ice sheet which could have fast responses. And if you pour concrete, your timescale is decadal because at some point you rebuild. The second point here are storm surges, which of course is important because a storm surge can drive water levels. There's also how much you build, how much you emit with your emissions, and what's the climate sensitivity. Those interact, which are the bars, but just to point out, there are certain uncertainties that are maybe important for other questions if you have a longer time scales. But for this specific question, you can actually focus the analysis on those uncertainties which are more important. And with that, I will stop sharing my screen and hope looking forward to the questions. Thank you very much. Jerry, I think you're muted.
Thank you, Klaus, for cluing me in on that. Our next speaker is Melanie Luck-Vogel. She is Senior Researcher at the Council for Scientific and Industrial Research of South Africa. She was educated first in biological sciences at the University of Bonn and later received her PhD in geography and remote sensing from the Julius Maximilians Universität in Würzburg. Her key activities are in the development of remote sensing tools and applications for integrated coastal management and climate change adaptation, and also the assessment of vegetation characteristics and dynamics using ecological and remote sensing techniques. These activities have produced dozens of peer-reviewed articles, and we look forward to hearing about her latest results today. So Melanie, please.
Yeah, so let me quickly share my screen. Good. Can you see it?
Yes, we see your screen.
Okay, cool. Good. Yeah, so my presentation is focusing a bit on this point which Klaus mentioned. So how can we translate scientific information into something useful for decision makers? So let me show you some examples from Africa, South Africa in this case. So these are actually recorded sea level rates over the last decades. And then you see it, so this is quite in line with the figures that John Englander showed at the beginning. So our sea level rise rates actually differ around the coast. And during the decade or the decades until they were measured until 2009, it's pretty much in line with these figures which John Englander also showed. So what we do is to inform our decision makers is we take sea level rise scenarios and project them inland. So you see here we used in this tool, in the OSIM's Coastal Flood Hazard decision support tool, we used kind of relatively generic flood models of 30 centimeters, 61 meter and 2 meters, just to illustrate which areas might be affected if no adaptation or no flood walls or whatever will be produced. So this tool and the coverage of these data we have available for about 50% of the South African coastline. The other thing which is important for decision makers is how do we prioritize areas? And so in our case, in another project, in the National Coastal Assessment Project, we actually overlaid different flood hazard scenarios. So these are focusing on floods in general, not just on sea level rise, and identified the number of buildings per per scenario and per risk zone. And we did that and compared that with building GIS data from 2011 and 2016. And while our flood layers remained exactly the same. And so now this is where decision makers get a bit worried, because you see that in only these 5 years, the total number of buildings in the different flood zones here actually almost doubled. What you see here, this is our provinces, the Northern Cape, the Western Cape, this is the Eastern Cape urbanized areas, and this is the Eastern Cape traditional areas. And the same for KwaZulu-Natal, urban and traditional areas. Areas which would be directly affected by sea level rise would fall in our very high risk category. And you see that currently, in 2011, we had very few buildings actually being present in this very high risk zone. And in 2016, while the number increased, I think on an international perspective, this is still relatively little. So to worry our decision makers even more, we have projections of how our population actually will grow in South Africa. This is from another project, the Green Book. And so what you see is all these dots are settlements. And the pinkish ones are those which will be seeing the highest population pressure and highest population increase during the next 30 years. And you see that apart from our capital area, Pretoria and Johannesburg, the most areas with the most development pressure is along the coasts. And this is partly related to the inland actually becoming less inhabitable and less favorable for instance, agricultural activities. So in fact, this area here, they expect the population in these settlements along the KwaZulu-Natal coast to double in the next 30 years. So this is now when you really start to worry about where are these people going to live. A while ago, we did a climate change risk assessment for Mozambique. And you see here the very broad scale assessment that we have got. And you see we have cyclone hazard, wave hazard, tide hazard, but we also have elevation vulnerability, which means actually it is flagging areas which are low lying. And here we see the area of Beira and these floodplains. So, and these will be very prone to sea level rise, obviously. And the situation for coastal risk in Mozambique is actually worse than in South Africa, because here in Mozambique, the coasts are actually relatively flat, as we can see from the elevation vulnerability. While in South Africa, our coasts are relatively steep. So over large parts of the coast. So that explains why actually we have relatively little buildings in South Africa in the high risk zones. So in Mozambique, we took actually the attempt of providing advice for adaptation to the extreme technical level as well. So you see for every kilometer or so of coast, the team of this project actually gave specific recommendations ranging from accept and retreat up to building groins, dikes and revetments and all kinds of high-tech protective measurements. Also for the area of Beira. But the problem that we saw in Beira is, so, and this project was done in 2012. So we provide these very detailed adaptation options, not just for Mozambique, I'm just using that as an example, but at the end, are they implemented? So you might be aware of these big floods in Beira, which we had in January of this year. Why does it happen if we actually provide this technical information? So the information is there, but the people need to do. So the question that we really have is, why is it not implemented? And so the reason for that are manifold. I think in many cases, it's probably that the government is of either the local governments or regional governments or national governments might feel uncomfortable in doing that. So either they don't have the funding actually to do these high-tech installations, or they don't have the capability just to even see through a tender process. Or maybe in some cases, the money which would be allocated for these purposes is used elsewhere. So how can we protect the people? And as you will hear in the next presentation, so it's frequently the poor people which live in the most flood-exposed areas. And what can we do to protect them from sea level rise? And so the question there would be, can we not maybe consider informing these people so that they can take some action on themselves? So I want to give you an example where that worked. What you see here is actually, it's a flyer, which was created after a massive flood that we had in 2007 in KwaZulu-Natal, which is the east coast of South Africa. And major storm, and you see the erosion in this case was the biggest problem. But they produced this little flyer actually to inform the public of what the risks are. And also what we see, especially in our South African very poor areas, is that the people actually starting to help themselves. So in some of our flood-prone areas in Cape Town, the people, the informal settlement people actually start to build their houses on stilts, or they build drainage systems through their shacks. So if the water comes, that it can go out very quickly. And so that might be something to consider, maybe linking it with online maps with our risk lines, and then give very basic information of what the people might be advised to do. But that's my question that we might be able to discuss in the discussion section afterwards. So that was my presentation. And this is a view on our beautiful Cape Town. And thank you very much.
Great, thank you, Melanie. Very interesting presentation. Now we will move to our last presenter. Hans-Peter Plag is Professor of Ocean, Earth, and Atmospheric Sciences at Old Dominion University. His research includes sustainability of the anthroposphere, global and climate change mitigation and adaptation, sea level fluctuations and impacts on human ecosystems, and addressing variations on scales ranging from global to local. I'm particularly pleased to have Hans-Peter with us on this panel because he is in Norfolk, Virginia, where sea level rise is an increasingly important issue, including in my old neighborhood from when I was on the faculty at Old Dominion. Hans-Peter, take it away.
Okay, thank you, Jerry, for the introduction. What I would like to do is to talk about the ethical challenges we are facing in adapting the urban coast, particularly the urban coast for the post-Holocene, and for in a time where we are facing Anthropocene risks. These are the really great risks we have created, and they all are interlinked, and we cannot look at one of the risks without looking at all of them. And adding to what you said about me, I have to say that over the last 4 or 5 years, I've been intensely involved with students working on sustainability leadership and conservation leadership. And when you do that, you have to look into, for example, psychology biases, that we have cognitive biases, economy, philosophy, many other things. So you have to really look at things, among others, from ethics. And the 2 ethical principles that I have in mind, I will not talk explicitly about them, but I have in mind those 2 ethical principles in what I'm going to say. And one is a duty not to participate in creating massive harm, and the other one, a duty to do justice. And I think our society today is based on those normative ethical principles, even if we don't follow them. For example, we don't like it if a country commits genocide, massive harm. We don't like that. We normally judge this as not acceptable. And so the one thing that I want to start with is to talk about a normalcy bias that we are suffering from. And it came a little bit out of what John and Richard said. We have been going through the Holocene. The Holocene was extremely stable in terms of climate, and it became stable after almost 4,000 years after the temperature became stable, sea level became stable, and we suddenly were able to move into river deltas and to build settlements in river deltas and benefit from this extreme situation. So the Holocene was a safe operating space for humanity, and it is changing now because of a situation that we have created. And I take it as very important that distance determines the perspective we have. And over the last few years, I have taken a position where I approach Earth in a spaceship as an alien, and I look at Earth from this perspective. And what I see is a life support system for a complex web of life, aiming for homeostasis, and the global essential variable that I would apply to any other planet as well is the energy imbalance. How large is the difference between incoming and outgoing energy? And for a healthy planet, it's very small. For Earth, over a long time, averaged, it was on the order of 10 to the minus 10, 10 to the minus 9 or 11. And I would take out my instruments and measure this for this planet and would find out it's 3 times 10 to the power of minus 3. And for me, it would be very clear this planet is an extreme catastrophic trouble. A planet that has an energy imbalance of this order, which is not happening in Earth's history, basically, is in real trouble. And for me as alien, it would be very easy to find out it's a single species that's doing this, and it's not the dolphins, it's not the whales, it's Homo sapien. So that would be not a problem. We look at the energy imbalance over 200 million years. The planet stored something on the order of 100 to 1,000 zettajoules. And then one species came along and used this to actually change the energy imbalance to 3 times 10 to the minus 3. And to really show you what this means is the planet is currently storing 1,000 zettajoules in 1 century, not in 200 million years, but in 1 century. That shows you the scale of what we are going through. And so the Earth's energy imbalance increased by a factor of on the order of 1 million to 10 million times. And then we would also see that it all goes mainly into the ocean. We are heating the ocean. So I sometimes say we are not living in a greenhouse. We are actually living in a pool house with an enormous pool. And we are heating this pool. And as you all know, if you are in a greenhouse and you close the windows, it gets hot immediately. In a pool house, no, it stays cool for a long time until the swimming pool has been heated. But this is happening right now with on the order of 320 terawatt. And that's 15 times the total global energy usage of humanity. So our changes in the physiology of the planet have had an amplifying effect to what is happening with the planet. So with the high inertial in the climate system, the system is heading to a totally different state. And Richard, you pointed this out a little bit. It takes time to melt the ice. But what we know is the ice will melt. There's no question, most of the ice will melt. We are heading for a planet that has a very different equilibrium ice sheet compared or in equilibrium with the temperature. So we will have sometimes, we will have in the future 30, 40, 50 meters of sea level rise. The only thing we don't know, we know the future that we get, but we don't know when will we get it. So is this the time scale for the sea level, or is it going to happen much faster, or is it happening even faster? We don't know that yet, but we know what the future is. Sea level will rise by many tens of meters. So is this potentially a global catastrophe? I would say no, it's simply geometry. Any animal, almost any animal, knows if my habitat gets inundated, I have to move. It's very simple. Every animal knows, almost every animal knows what to do. Humans are different from other animals. We have limited foresight, precaution, imagination, and we suffer from probability neglect. Under uncertainty, and we heard this in another presentation, we make really weird decisions. So we populate the coastal zone and design the built environment as if sea level would never rise. We do this every day now. I see this here in Norfolk. They are building like sea level is never going to rise, is never going to rise. So this creates a global catastrophe, a catastrophic risk, not for us today, but for future generations with the potential of massive harm and widespread injustice. When the Romans built their buildings, they didn't think about us 2,000 years later, but what they did is not impacting us because it was natural material. And if a Roman building goes into the ocean, the fish are just happy because they found a new habitat. This is very different for human beings. And when you look at how our cities are evolving in the coastal zone, it is an enormous threat that we are building for future generations. And we introduce new materials. One new material that we introduce is plastic, and 45% of the plastic goes into construction. So it goes into the buildings we build. And plastic is very different in future generations than a stone building. So when you look at this, only the last number down there is important. The coastal built environment by 2045 will have probably 1.7 billion tons of plastic. And most of that is in the coastal zone waiting for inundation. So when we really think about the future generations, and my estimate is that there could be something like 500 billion people in the next 5,000 years that are being born. They are impacted by our decisions today. And so the plastic crisis, in my opinion, is infringing on their rights. So when we look at the role of Homo sapien, I compared us to big natural events, Toba eruption, Tambora eruption, earthquakes, and you see the recurrence time at the bottom in 10 to the power of the numbers. And when you put in Homo sapiens, for 1 year, we are comparable to several Tambora eruptions. We are comparable to a Toba eruption in terms of energy. So it's not the question, where is the energy coming from? It's the question, what are we doing with the energy we are using to the planetary system? That's more important than actually where the energy comes from. So looking at this, I came up with the idea Homo sapiens is a cataclysmic virus in the Earth's life support system. And that brings me to the question, post-pandemic or actually pandemic? And when you look at the comparison, coronavirus, human and Earth's life support system, then when we look at the size, the ratio of host to virus is almost exactly the same for human to corona and Earth to human virus. So we have the same ratio. The impact is very comparable, but a very big difference is the coronavirus has 8 billion hosts to jump around. So if one dies, it's not a big problem. We have only one host. We can think that we can go to Mars and terraform Mars, but we have basically only one host, and we need to be careful to behave like a cataclysmic virus in this thing. And for me, the question that I discuss with my students is, can the virus transform itself into the healer? And for that, of course, we have to think about how we actually live in the coastal zone. That brings me to paradigm that limit the options that we are actually considering. And the sea level paradigm that comes out of the Holocene is sea level is stable, coastlines don't move horizontally. That's what we think when we build in the coastal zone. And I propose that we need to actually have a paradigm based on foresight. Sea level changes a lot. Coastlines do move horizontally, a lot, maybe very much. And that would mean that we don't have to look at these things here in the way we do. It's not maybe New York, But we know already that most likely Jakarta may look like this by the end of the century because subsidence is very, very high. In some areas, it's 25 centimeters per year, which means in 100 years, it will be 25 meters below sea level. So Jakarta is going to be moved, but what are we leaving behind? Are we leaving behind a huge amount? Or do we think about future generations in the same way as we think for nuclear warnings in the future generations, where we think about we need to inform them later about what is happening so that they are not running in problems with nuclear waste? Are we doing the same for the urban coast or not? Well, I would say that if we accept this new paradigm, then we have to do some fundamental consequences how we build in the coastal zone. We need to redefine what real estate is. We need to design the urban coast with a design principle for future inundations. We need to anticipate new extreme events, adaptive infrastructure that can move with the coastal zone, live where it is safe, and work where it's needed. We have the means to do the transportation between these two locations, redistribute risk, and take responsible for future generations. Maybe we need a convention about the urban coast, where we not leave it to one country to decide what they do, but where humanity thinks about the risk we are creating for future generations. So we need to constrain the present to liberate the future. And when I was 20 years old, I saw this movie. I don't know whether you know where this is from. It's from the Planet of Apes. This is the last statement, what is being made. You maniacs, you blew it up. And when I was 20 years, this was our big thought. Are we going to blow up the planet with a nuclear war? And we were very worried about. My students asked me what I would tell my 20-year-old self today. And today I would say, we need to really think about the Anthropocene risks that we are creating, and we need to do all we can to avoid them to be a problem for future generations, so that our future generations are not telling something like this about us. I think we have a legacy to create here for future generations that makes it possible for them to have a future that is comparable to our future. Thank you.
Yes, and thank you, Hans-Peter. I not only for the informative presentation, but for the charge to us to do better with respect to future generations. Well, we've had an inspiring hour of presentations. We have heard from John on a number of facts. He showed interesting time series that I think are great for communicating to the public. We heard from Richard on some of the underpinning science. We heard from Klaus also on science, but also dragons, and I want to return to the dragons in a few minutes. Melanie told us about developments in South Africa and nearby regions, and we'll return to that in a little bit. Hans-Peter reminded us or informed us that we live in a pool house, not a greenhouse, and that we humans need to do better as we live in that pool house. I have a number of questions that I want to put to the panel, some to individual panelists and others to the panel as a whole. We also have a number of questions coming in through the chat box, and we'll get to those in a few minutes. Let me start by following up on one of the perceptions that I came away with from one of John's slides. John, you showed an interesting slide with 3 time series. I think on the top it was the history of CO2 measurements. In the middle was temperature, and on the bottom was sea level. Of course, on the CO2 graph, you come up to the present day, and suddenly the line shoots up towards the sky, reflecting our rapid increase in CO2 in recent decades. At the end of the temperature graph, you showed a little blip upwards, And this is relative, sort of percent relative to the variation over preceding millennia. And on sea level, it was as yet almost imperceptible in your graphic. I think this is, this is part of the problem. Humans are accustomed to looking at those kinds of time series and sort of making an instantaneous judgment. Is the present day within the norm or not? I think people are becoming accustomed to the fact that CO2 levels are not within the norm. There's some argument about temperature, and for sea level, well, let me put it this way. I have a sister who lives in a beach community, and she is completely unconcerned about sea level rise because she lives, I think it's 5 blocks inland. And she says, well, if the sea level goes up by 2 or 3 feet, I'm far inland. It makes no difference to me. She lacks the perception of what even a modest sea level rise will mean for her personally and for her children in the future. So John, talk to us a little bit about your communication strategies with the general public. How can we bring home in a way that matters on a personal level the sorts of information that we've been discussing here today? How can we make that real for individuals?
Sure. No, great question. And and this ties in very much with Hans Peter and Melanie and Klaus talking about how do we play this forward, and how do we and Richard as well, how do we explain this? I find in talking to broad audiences, keep the language as simple as possible. Don't even use jargon about mitigation and things like that. It's slowing the warming, reducing the flooding, use very, very plain language. And in terms of connecting to your question, Jerry, I like to ask that we think out 30 years. The usual milestone for climate of the year 2100, 80 years from now, is just way too far in the future. And most people, of course, don't even want to think out 30 years, but 30 years is a home mortgage. It's when most people's current lifetime, if anybody's alive today, it's certainly a generation. And in 30 years, we could start to see 1.5 feet of sea level rise, according to some of the projections now. And I ask people to think about the legacy they leave in their grandkids. And I find that punctures the balloon for most people. People will say, oh, why should I care? I'm 82 years old and I won't be around. I say, well, do you have grandkids or kids? And most people say yes, or even nieces and nephews. And when you put in the context of how will we be remembered, just in the plainest language possible and the most emotive, it actually does pop the bubble for most people.
Great, thank you, John. Now, of course, we do need some people working way down in the weeds of the science, using to great effect the scientific jargon and so forth. So I'd like to ask Richard, what do you think needs to be added or tuned up next in the models that the IPCC will use going forward? Where are the deficiencies in our science and modeling capabilities today, so that we can do a better job in the future?
The biggest issues are breaking things, to be honest. There's several issues, but the biggest ones are breaking things. I have a graduate level minor in metallurgical engineering, and said calculate everything to 5 significant figures and then build it 3 times stronger, because you'll never get it right to a factor of 2. I have a coffee mug here. If I threw it on the floor, what would happen? Right? And it might chip, and it might break in 2, and it might bounce, and it might break into 1,000,000 pieces. And I could very accurately predict the average behavior of a whole lot of coffee cups. I could do a Bayesian version, simulate different people dropping coffee cups all over the world. Can I predict one coffee cup? And will the ice shelf break off? Will the cliff break on this glacier that has 3 meters of sea level behind it? Is a really, really hard problem. And the worry is that there'll always be some range of uncertainty. So we're going to try, we're going to throw the best science at it. It's happening. There's brilliant people working on this, but you have to recognize just how hard the problem is. A huge amount of engineering is nothing but trying to stay away from fracture mechanics. If you have to really worry about how fast your bridge is breaking, you failed. And we have to worry about how fast this cliff is breaking at Thwaites Glacier.
Good point. Thank you, Richard. Klaus, you were talking about uncertainties and the uncertainty about uncertainty. And you referred to dragons. I normally think of that as demons, not dragons. But tell us a little more about that. What's being done to slay the dragons that bedevil us with uncertainty?
Excellent question. Thank you. The point here is to recognize that if you ask Richard about how likely is it, he just said, well, for this cup, I don't really know. I can know about 100 cups. And if you ask other scientists, equally smart as Richard, is hard to find. But if you ask other scientists, they give you different answers. So the point is, you ask 2 scientists, you get 3 answers. And it's not because they're not smart. They are really, really smart. It is just that some find this is unknowable. And it might help, we live in COVID times, to compare this to, I talked to my favorite doctor and about the COVID risk, and he says, well, it's really hard. It's dangerous. We know it's dangerous. Here are a few things. You don't want to take those deeply uncertain gambles. And then you take the best advice and say, how do you stay away? Of course, staying away has costs, and navigating those trade-offs between costs and safety is really, really hard. So I think, to summarize here, it's important to characterize the dragons, how they might look like, to the best of our ability, to recognize whether some of those uncertainties can be resolved before we have to make a decision. But it turns out that for many decisions right now, where people have to elevate a house or have to build, we cannot wait for better science, because better science takes 3, 5, 10, 15, 20 years. They have to make decisions right now. And so the question is, how do you make decisions under deep and dynamic uncertainties, which is really hard? And another point to Hans-Peter and to Melanie's comment here, it is important to hone a scientific enterprise, and I'm 100% for that. But it's also important that all the power in this machinery gets on the road. It's a translation between the science and decision-making. How do we communicate it that it's salient and people actually recognize it? The point you brought up, are there better ways to explain it something? Are there better ways to engage with engineers that they build better things? How do we deal with this? It seems we live in different times, and how to make rules and guidance in different times, I think, is one of the challenges. Thank you.
Great, thank you. And I want to turn now to Melanie. Melanie, you mentioned a sad but interesting story in South Africa. You said that that inland South Africa is becoming less habitable, and this is causing migration to the coast, and some of that migration is going into areas that will be affected by sea level rise. So this kind of geographic squeezing of the population into dangerous zones, and it intrigues me. First, tell us what actually is driving that migration from inland. I assume it has to do with climate change, but is it simply the heat? Is it change in rainfall? Is it land degradation? What's driving the migration? And then as those people make a transition towards the coast, how do you see that reflected in local economies and such? So talk to us a bit more about that.
So the inland areas in South Africa are actually agricultural. And so a lot of that at the moment is cattle farming and livestock farming. And the inland is getting drier and hotter. So livestock farming will get more difficult. And our climate forecast for South Africa says that especially the eastern parts and the eastern coastal parts will get wetter. So we will get even more rain, which might be beneficial for agriculture, such as sugarcane as well and fruits. So there is a lot of, in the eastern part of South Africa, on the South African coast, there's a lot of very high value crops. There's a lot of fruit production as well going on there, and sugarcane. And so this is where the people go, according to our calculations in the Green Book, which you can Google. And yeah, so this is a problem. But again, I think having risk lines like the ones which I presented, having them in place for especially the local governments is actually an opportunity. Because we can advise them straight away, even before the areas are actually developed. Hold on, we have a very high flood risk here. Rather make sure you do not develop here and keep the people out. So this is actually the beauty of these projections inland. Does it answer your question?
I think it gets there. Let me, and we'll come back to this in a moment when we go to the audience Q&A. But now, Hans-Peter, you made the statement that we're building as if sea level will never rise. Of course, we see that all around the US coastline, but we also see it in a major way in China. Just a few years ago, I read an amazing statistic that I think it was between the years 2011 and 2014, China poured as much concrete as the US had poured in the previous 100 years. Such is the scale of rapid development in China, much of which is in their coastal areas. So when you build cities, building streets, sewers, water systems, etc., you are not only baking in the location, you are baking in the demand for power, the demand for natural resources, which have to be delivered and utilized in coastal areas. I know in Norfolk, for instance, there has been some discussion about moving city infrastructure away from the streets that border the rivers, marshes, and estuaries. Do you see this happening? Is that getting traction? Is it happening on the local basis there in Norfolk?
Well, I would say it is really not happening at any reasonable scale. And when you think about, I saw an estimate that in the next 30 years, we have to build as much as humanity built in the last 6,000 years. And that is giving us the scale of the problem. If we build, as we are building today, this amount of buildings, and many of them in the coastal zone, we build the marine debris of the future. We are seeing already that, for example, the 2011 tsunami in Japan took as much marine debris into the ocean as humanity does in a whole year. What is happening at the south coast of the United States now, we get marine debris again and again. And as I said earlier, when buildings were built, even like the people built Venice, even when Venice goes into the ocean, it will not be a big problem for the marine biosphere. But what we are doing today is creating a problem for the marine biosphere and going to degrade the marine biosphere at an enormous amount. And so I think that we need to think about how are we building into the coastal zone? I'm not saying we need to move out of the coastal zone because the benefits are extreme being in the coastal zone, but we can build in a way, and I'm working, for example, with some engineering companies to think about whether we can build buildings that can easily be deconstructed and then taken somewhere else and be reconstructed. You know, as kids, we all play with Lego. Why can't we build buildings in the same way so that the individual blocks can be taken easily apart and then moved somewhere else? Concrete is a different problem because of the carbon dioxide emissions that we have. Once it is in place and once it is clean as concrete in place, it's not going to be a problem for the future. It will degrade and become, you know, a normal material again. But what we put in with our electronics, with plastic, that is a problem for the future generations. And I pointed out that we take responsible for our nuclear waste, but we don't take in the same way responsibility for the urban coast we are building and what it's going to do to the marine biosphere and then coming back to humanity through this channel in future generations. And I think that that would require that we start to think with a different paradigm of how we build the coast. And even more important, I think we need to look at ourselves and try to understand who we actually are in this planetary life support system. And if we don't understand that, I think we will not change things significantly to avoid the global risks.